This thing here is our liquid helium apparatus. We're going to use it to cool liquid helium until it turns into a superfluid. Superfluids are a state of matter that is very much like a liquid, but it has zero viscosity and infinite thermal conductivity. So it exhibits some unique and interesting behaviors that we're going to look at. Now, the reason we need such an intricate apparatus is because liquid helium boils at 4 Kelvin, and it becomes a superfluid at 2.18 Kelvin. So it needs to be extremely well insulated to keep heat from getting in. And it's in a glass dewar, which is the only way we can observe it by eye, but even glass lets in a lot of light, which can heat up our fluid. So we start with our big inner dewar, which we're going to fill with liquid helium. The container that the liquid helium is in is a vacuum jacket. So we're going to pump all of the air out of this, so that the only place the helium can exchange heat is up here at the top. Then for added measure, we're going to put all of this inside of another jacket. And we're going to fill this one with liquid nitrogen. So this will help pre-cool the inner jacket, because heat transfer is proportional to temperature difference, and liquid nitrogen boils at 77 Kelvin. Then what we're going to do is suck all the air out of the inner jacket. As long as there's air up here, it's going to be way too hot for that liquid helium. So the helium is going to be boiling constantly. Once we get rid of all the regular air and the boiled off helium in this chamber, there will be no material left in here to heat up the helium. At that point, we can just use evaporative cooling to cool the helium down from 4 Kelvin to 2 Kelvin. By this point, the only places that the helium can exchange heat are through what little vapor evaporates out here and through the tops of the dewar. The superfluid helium experiment is one of our more complicated demonstrations. So I'll be working on it together with Professor Brad Philippone, who's teaching our statistical mechanics course this term, as well as Dr. Wang-Chun Wei, who's a research engineer with a lot of experience with liquid helium. Professor Philippone will be explaining the phenomena we see along the way.
So we're about to transfer liquid helium into the central volume. We've got liquid nitrogen cooling the outer jacket. We're now going to transfer helium from this dewar here. It's full of 65 liters of liquid helium at close to 4 Kelvin, and we're going to try to get some liquid to go inside. So we're now going to lower this transfer line, which is at room temperature, into the helium. So the first thing that's going to happen is going to raise the pressure inside significantly. So the helium will eventually come out of this tube at the bottom. Oh, yeah. Oh, it's better. You can see it. Yeah. Yeah, okay. So that's helium coming out. At some point, I want you to check the, watch the level. I want to zoom in both cameras to the level. I don't see it. Oh, there it is. Oh, yeah, it's going up rapidly. Okay. Tell me, can you tell them when to stop? You want to go, you're saying up to here or something?
Yeah, pretty high.
I can sort of see it on here, actually.
Oh yeah, you can see it easily on that.
Want to zoom out that a little bit?
that's his phone light.
Yeah,
What if we turned on
that's
one of
better.
these?
Look at that. See, that's what we had before. We had a, yeah.
There. I turned on one of these. And I'm turning on
Lower down.
the other one.
Lower down the
There, look. Is it, what's the temperature?
It's at 39 Kelvin, 2.18, or 2.18 Kelvin, 39 torr.
2.17 is the transition. Don't touch the table. We're seeing a little bit of vibration, but I think that's from the pump. That's just the surface. So the bubbles have completely stopped because the thermal conductivity is essentially arbitrarily high, so there can't be any gradients, temperature gradients, because of the superfluid, because it has such a high thermal conductivity. So that means there's some fraction of that liquid is actually superfluid right now. So you're really, really close. Okay, watch, you'll see what, yeah.
There it goes.
Watch, there. There's
There it goes.
Oh, nice, that's it.
Wow.
2.17.
2.17. The calibration might be off 0.0.
Yeah.
Calibration might be off a bit.
Yeah.
Well, that's pretty good.
Is this
Watch the
fast?
balls up. Nice. Superfluid. 2.17.
Yes.
So I'm going to lower the first demonstration in. You'll see a little device fall in. Look at that liquid level. Oh, it's because of me moving the whole thing around. Am I touching?
Yeah, a little bit.
Is that better angle?
The other way.
The other way?
You want better angle? Okay, that's the top facing the camera.
Yeah. Now I can. So you see that white thing, and there's a little tiny resistor, which I'll explain in just a second. So I usually go. That should be enough, right? Okay, so let's see if we can. So what we have, this is the liquid helium level here. It's clearly at a temperature of less than 2.17, so there's some fraction of superfluid. What we have is a very tiny pore filter. This filter, because of the viscosity of the normal helium, it cannot pass through the small holes. So only the superfluid goes in there. So you fill this with superfluid, okay? So the normal fluid, there's still a fraction of normal and a fraction of superfluid. Only the superfluid is filling in here. But what I'm going to do is, I have this power supply hooked up to a resistor. By turning the heater on, I can go make the temperature of the helium inside here higher than 2.17, the transition temperature. And so that means there's no more superfluid in here. There's no more superfluid. We have a huge gradient. I have superfluid here, none in here, so the superfluid flows in. It keeps flowing in. As I turn it, as it flows in, it gets hot, turns to helium. I ran out of superfluid. So it keeps coming in until you think the level would be there, but it keeps pushing up. The normal fluid comes out until it comes out the top. And so the viscosity of normal fluid prevents it from passing the filter. So when there's a little bit of normal in here and a little bit of superfluid, the normal won't go up. When I make this all normal, the normal can't go down because it can't get through the filter. So this volume fills up until it comes out the top and more superfluid falls in. So that's what we're going to try to see. So, oh yeah, I'm moving it right there. Okay, use your finger or something if you can. Yeah. Oops. Yeah, there's the meniscus. Okay, now you follow it with the camera if you can. I'm raising it well above the liquid. Okay, go, 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 go. There. It's dripping out. I'm at 3.5. This is just where it's supposed to be. There, look, look, look. There, there, there. I need some backlighting maybe, but that's not too bad. No, that's worse. That's it. Yeah, see that? Here's the fountain. I can maximize the fountain. There. Ooh. Voltage going up. I'm I'm getting more, I'm converting. When I get high enough, I'll convert all of the superfluid to a normal, and then I'll just keep flowing in arbitrary amounts. So you're going to back out. See that? Okay, you see the line? Oh, that's going up fast, going up to the top, and ooh, I see a little bit there. I think we have the bad angle.
No, it's coming out now.
Oh, there we go. Okay, I need the light change.
Yeah.
The index refraction is not. Yeah, there.
Might give you
The liquid,
the
there's
polarity
a
of it,
tip right there. You see this
contrast.
plume of liquid that's flowing off to the side. So I can lower it. I'll just change the voltage. I can make it smaller. There's a little tiny bit. Is that visible to everybody? You see it? Okay, cool. Okay. So that's it's called superfluid creep. The interaction between the helium-4 and the helium-4 and the helium-4 and the glass, we're going to have what we're going to do is we have a little beaker. We're going to fill it with helium. But what happens is when the interaction of the helium with the glass, it's just a molecular, it's a atomic molecular physics question of whether the attraction between the helium and the glass is bigger than the helium and the helium. So what happens is, the helium coats the glass. And if the glass has a top, it coats the glass, it keeps coating the glass, both sides. It coats the glass all the way through. It keeps coming out until there's so much here that gravity causes it to fall off. So we're going to see if we can force the helium. In principle, the helium can keep flowing until it's emptied out of the beaker. The lighting is terrible. I can change the focus if... Ooh, something's dripping. I see it. 1, 2, there. See it? 2, 3, 4. Do you need a little bit better focus, I think?
Yeah, you can.
We see the drips. Did I lose it?
You know,
There.
perfect.
Oh, there's a big drop. Look at that. Yes. It will eventually slow down because the helium, if less and less superfluid is in the cup, there's less of it to climb out. And when you're not in the liquid, it's still dripping though, but it's taking a longer time, right? A little bit of liquid right at the very top. Okay. Drip, drip, drip. Oh wait, the light. I can't see the drips. You gotta optimize my light. There we go. Drip,
I don't think it's dripping
drip,
right now.
drip, 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 drip. Is it cold enough? Drip, drip, drip. So it's flowing off the side. Eventually, as long as it stays cold enough, it will have some constant drip rate, and eventually I can empty it out. It's liquid on the surface of it.
It's full.
Yeah, it's full. But notice it's dripping, so it's just getting a little extra. But then watch, drip, drip, drip. It should slow down once all the helium is. But no, it doesn't slow down. Drip, 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 drip.
So